Greetings, traveler. I'm the calculus cleric, and today we'll be working on Taylor's series. So the problem is to find the Maclaurin series and find the interval on which the expansion is valid of f of x. Now, so basically what this problem wants us to do is 1, find the Maclaurin series, and 2, find the interval, or the interval of convergence, you could say. And so what I'll do first is find the Taylor polynomial of f of x, which is we just bring the f of x down of cosine 3x. And because it's given to us that this is a Maclaurin series, we know that our a value is equal to 0, or just what we plug into x. That's what a is. Then you multiply by 0 is 0. Cosine of 0 is 1. And then you find the derivative of whatever function's above it. So we do Taylor polynomials again. Sine 3x. Chain rule the 3 out. Replace x with 0. This is equal to 0. So 0 multiplied by 3 is also 0. So we just get a total of 0. And then we find the second order derivative. And then the third order derivative. And then to top it off, the fourth order derivative. I typically take out my Taylor polynomials to the fourth degree because it makes it a lot easier for me to see the patterns that are required later. And from there, we just combine that into a Taylor polynomial. It's not a Taylor series yet because it's not infinite. It's in terms of degrees. This is what it's supposed to be, but I can simplify that and just call that x. Okay, so now to figure out a Taylor series, first we must figure out what f of n is. And basically, we're just trying to find a pattern between all these values so we can sum it all up and make a general term for what happens when we go out to like the 100th degree or something. But right away, we'll notice a problem, mainly with these zeros. So when this arises, you can't really figure out a pattern for these sums because that will require you to have two functions because that will be a 0, and you can't get a non-zero value out of a 0. So we'll have to create a new Taylor polynomial where we just exclude all the zeros. That way our pattern finding can be made easier. Keep in mind that when we do this, our terms will shift. So this will go from being the fourth term to in here it's the second term. So we have to keep in mind that and not treat it like the fourth term, even though it obviously looks like a fourth term. So let's go work on finding what that f of n is by figuring out the patterns here. So let's break this up into steps because there are four things that it looks like I need to look for. Let's start with the easiest, which is typically the variables. When this n is 1, how do I get that equal to n squared? Well, if I get x to the nth, then I just multiply that n by 2. I can get an easy answer of x squared, and then plug 2 there into n for this to check, and that's x to the fourth power. So that checks out quite nicely. So we can incorporate that into our rule. basic terminology, when we have variables, we'll get an x to the nth power of some kind when we write it out to find the pattern. And when we look at these factorials, as I will show, it'll just be a number multiplied by an n term. And so let's do the factorials next, seeing as they're the most easiest. We'll notice that it also goes by even terms. So when this is 1, it'll be 2. When n is 2, it'll be 4. And so we can just say, looks like that. Because if we were to take this out some other degree, it could change your predicted pattern. So if I really want to be sure for this problem, I'd probably take this out to the sixth derivative, which would be equal to negative 729. When we slap that on here, it'll be negative 729 x to the sixth over 6 factorial, because there's actually another 0 in the middle here due to the fifth derivative. So we can just add that on there. And so you can see if we did it 2nth to the factorial and we did third term, it will be 8 factorial. So that's wrong. So we might want to take it out to more degree digits when there are zeros involved. Just a heads up warning. Add that into there. And lastly, we'll look at this before we move on to symbols. Our coefficients. So if you notice with these coefficients, they're also by powers. 9 to the 1th, 9 squared, 9 cubed. Yes, 9 cubed is 729. Fun fact. So it'd be 9 to the nth, because when n is 1, it's 9, 2, 81, so on. And lastly, we look at these symbols, noticing that it changes from positive to negative. So we need something in our rule for that. And basically, there is a one for all rule for this, which is negative 1 to the nth, and you just play around with that nth term. So like if I move the negative sign here, for example, I would have to make it so that when it was even, it would be a negative. So I just add 1 or subtract 1. But since this is on the odd term, when n is equal to 1, we can just leave this as it is, because when it's 1, it'll be negative 1. When it's 2, it'll square out and it'll cancel, and so on and so forth. That's our f of n. And so basically what we can do is we can stick a sigma sign in front of it, which means sum of, because we're taking a sum of this formula. Let me arrange it the way that most people do. And we're taking this out to infinity, because that's what a Taylor series goes to, infinity. And we have to determine the degree that we start at. So n is equal to some number. Well, we want to start at 0th term, because that's where we started here. It just makes our lives much more simpler, and it makes this rule true. Because when I plug in 0 into here, for example, because we start at 0, we'll get 1. Oh, and for those of you out there who just want to know why I allowed a 0 in the denominator, it's because when we do that, 0 factorial is surprisingly equal to 1. And so that is our Maclaurin series, and that's the first part of the question. So on to our second step, where we determine the interval of convergence. And to do that, we'll use our friend, the handy-dandy ratio test, because this looks just like a power series to me, even though it's a Maclaurin series. And basically for a power series, we'll just treat this like a of n instead of f of n. And we'll just apply the ratio test formula, which is an plus 1 over an when the limit of n approaches infinity. Let's write out our an values on our an plus 1 value first. Our an value is just going to be what's inside the series that we just found. An plus 1 is going to be equal to that, but you just replace all the n variables with an n plus 1. Be careful that we put it in parentheses so we remember to distribute. Okay, now we just plug our a n plus 1 and our a of n back into this ratio test equation. Well, first, what I would like to do is teach you another shortcut to make your lives a lot easier. When we do ratio tests, what I like to do is break up these things back into its individual components, so that way it's a lot easier to handle the multiplication between the two fractions that'll happen. You'll be able to cancel a lot of terms, hopefully end up with no n terms afterwards, make our lives so much easier. Remember that when we break this up into its respective components, it'll be the same thing as -1 n. When you multiply terms with the same bases, you can add their exponents together. And then with factorials, we can do this thing where we can break up a 5 factorial, say, into a 5 multiplied by 4 factorial, because 4 factorial is 4 by 3 by 2 by 1. 5 factorial is 5 by 4 by 3 by 2 by 1. So we can just take out a 5, call it 5 by 4 factorial. You see the same thing for this. You can factor out the 2n plus 2 and a 2n plus 1. And just leave the 2n factorial as is, because there's a 2n factorial over there. And we plug that in now. And what I'm going to do is, before we plug that in, I'm just going to cross off these -1 stuff, because we're going to be absolute valuing it anyways, which means that they won't factor into this at all, because negatives get canceled out by an absolute value. So it's of no importance here for this ratio test anyways. And then now we can cancel out a lot of terms. And that really paid off that we separated into its individual components, otherwise we have to worry about that over here. Or you wouldn't cancel out anything at all, which would make your life quite hard. And we're left with that. And now we can plug in infinity into these n values. And that'll leave us with 0, because remember, when it's infinity on the bottom and some number at the top, it'll get smaller and smaller and smaller until it gets 0. So approach 0. So that's our limit. And that's really helpful, because our ratio test tells us that if our ratio test is equal to 0, then it'll converge for all values of x. And so we can write this down more formally. Therefore, by the ratio test, our series that we found above converges for all real values of x.